In this video, we're going to look at scale factor enlargements of similar shapes. Two shapes are said to be mathematically similar if their shape is the same, but their sizes are different. We can say similar shapes or similar solids have the same proportions. We can use that fact to solve a range of different problems involving the length, the area, and the volume. If we start off now with three different cubes, we've got a 1 by 1 by 1, 2 by 2 by 2, and a 3 by 3 by 3. What I'm going to do is build up now a set of scale factors. So I'm going to have now, and we'll just block this off, we'll have the 1 by 1 by 1, the 2 by 2 by 2, and the 3 by 3 by 3. So what I'm going to look at are three different scale factors. The first one I'm going to look at is the linear. So when we're talking about linear, we're talking about one dimension. So this is now the 1 cubed. This is going to be the 2 cubed, and this is going to be the 3 cubed. We can see now that the length of this bottom is 1. The length of the bottom here is going to be 2. And we can say the length of the bottom right here is going to be 3. If we look at the scale factor enlargement of the linear part right here, so just in terms of the length, we can say that this is going to be 2 times by 1. It's twice as big. So the linear scale factor is 2. This one right here we can say is 3 times bigger. So the linear scale factor is going to be 3. If we now consider the area, what we're going to do is look at the total surface area. So if I think about this, we've got now 6 sides, each of area 1. So we're going to have now on here the area, the surface area that is, of 6. So 6 times by 1 squared. If we look at this one right here, we're going to have 4 and we're going to have 6 lots of that. Now that is going to give me in total on there 24. So the surface area of this one right here is going to give me 24. If we look at the relationship between these, this one is 4 times bigger. So what I'm going to say is that this is going to be 2 squared multiplied by the 6. Over time you'll see what I'm going to do in terms of building these up. If we look at this one right here, the surface area, each one is 9, we've got 6 of those, that's going to be 54. If we look at this, this is 9 times by 6, and we can say that that is 3 squared multiplied by the original. If we now look at the volume, what I'm going to do is work out the volume of each of these cubes. Remember, these are mathematically similar. They have the same shape, they just have different lengths. They're proportional. So if we look at the volume, we've got now the volume on the first one, well that's going to be 1 times 1 times 1, which is just 1. 2 cubed, or 2 to the power of 3, is going to give me 8. If I just look at this now, I could write this as 8 times by 1, or 2 to the power of 3 multiplied by the 1, which is the volume of the smaller one. If we look at this one right here, 3 times by 3 times by 3 is 27. If we think about this, this is 27 times by 1, which is going to give us now 3 cubed, or 3 to the power of 3, multiplied by the original volume. So what we can see here now, building up this table, is if we have a linear scale factor, we can see now that in this particular case, it's going to be 2 to the first power. If it's an area, it will be 2 squared. And if it's a volume, it will be 2 cubed. If we look at this linear scale factor, so now for one dimension, 3 to the power of 1, the area is 3 to the power of 2, and the volume is 3 to the power of 3. So what we can say is that this is the scale factor, this is going to be the scale factor squared, and this is going to be the scale factor cubed. If you want a little 1 there, you can do. So this is going to give me my scale factor for any particular one that I wanted to do. So if I wanted to do now a 4, and we could work out the area, the surface area, either by counting up, or we could simply go ahead and multiply this answer by 4 squared. So if we did that, if we had one of 4, let's say we had a cube of 4, we know that the length would be 4. We know that the area would be 4 squared times by the 6. So that would give me a total of 90. Let's just write this down. What's that going to be? 96. And then if we looked at the volume, it would be 4 cubed, which is going to give me 64 times by 1, which is 64. And you can see by simply using these scale factors, we can go ahead and work these out. So linear, it's just a scale factor. We've got now the area, it's a scale factor squared. Remember, this is the linear scale factor. And if we want the volume, we take the linear scale factor and cube it. So let's go ahead and answer some questions. We're told two similar cones have heights of 100 centimetres and 50 centimetres. So what we've got here, let's just go ahead and put these on. So this is going to be now 100 and this is going to be 50. It says if the volume of the smaller one is 1000 centimetres cubed, calculate the volume of the larger one. So what we can say then is the scale factor. So we've got now an SF. The linear scale factor is going to be 2. So we can say scale factor, and I'll just write it on here. We can say that the linear is going to be equal to 2. Therefore, what we're going to have is a volume scale factor. So volume is going to be equal to 2 cubed. So all I need to do is simply take 2 cubed, which is 8, and multiply it by the 1000, and that's going to give me 8,000 centimetres cubed. A common error is to simply double it up. Remember, we're taking the linear scale factor and we're simply cubing that and multiplying it by the volume of the smaller one. Often with these questions, it's nice to build up a table of values. For this one, it's fairly straightforward. We've got a nice scale factor. We cube that and multiply it by the 1000. In this one, we're told two similar boxes have corresponding sides of 6 centimetres and 4 centimetres. In part A, if the surface area of the smaller box is 50 centimetres squared, what is the surface area of the larger box? And in B, if the volume of the larger box is 50 centimetres cubed, what is the volume of the smaller box? So if you want, you can draw up a table of values. You certainly don't need to, but it might make your work slightly easier. So if we look at this now, we can put this on and we will have the following. So we're looking at the scale factor. So if we have the linear scale factor, we have the area scale factor, and we have the volume scale factor. What I'm going to say now is that we have and we could write this as a ratio, but this is going to be 1.5 times bigger. So I'm going from the small to the large. So from here, the small to the large is going to be 1.5 times bigger. If you're ever stuck, simply do the 6 divided by the 4, and that's going to give us 1.5, or 3 over 2. So the linear scale factor is 3 over 2. The area scale factor is going to be 3 over 2 squared, which is going to give us 9 over 4. The volume scale factor will be 3 over 2, which we need to cube, and that's going to give me 27 over 8. You can, of course, work in decimals if you like. I like working in fractions, but it's entirely up to you. So let's have a look at the first question. If the surface area of the smaller box is 50 centimetres squared, what is the surface area of the larger box? So we take the smaller box, which is 50, and we multiply it by the area scale factor, which is going to give us now 9 over 4. So in a calculator, we can go ahead and do that. So 50 multiplied now by 9 over 4, which is 2.25, and that will give us now the volume of the large box, and that is going to be 112.5. So 112.5, and that will be centimetres squared. So that's what we end up doing. We're now looking, it says, if the volume of the larger box is going to be 50 centimetres cubed, what is the volume of the smaller box? Well, all we need to do is simply divide. We've got our scale factor from going from small to large, and of course you could have done it the other way around. You could have written this as 2/3. So if you want, you can write this as 2/3 cubed, and that is going to be taking it from the large to the small. So what we could do is simply say now that the volume of the larger box is 50, and we're going to divide that by the scale factor of 3 over 2 cubed, which is going to give me 27 over 8. Or what you could have done, either or, exactly the same calculation, 50 multiplied by this one right here, which is the other way around, which is 8 over 27. Hopefully you can see those calculations are identical. So what's that going to give me? 400 over 27. And of course we're expecting this to get, if I do this one, 8 times by 50 is 400. 400 over 27. And that's going to give me now 14.81. So we'll say that's going to be 14.8, and I'll give that to one decimal place, and that will be centimetres cubed, which is what we would expect. Now if you think about this, if we went ahead and multiply that, we know that multiplying this now by the scale factor of 1.5 cubed, that is going to go ahead and give us exactly what we were expecting, which is the 50. So as you can see, being versatile, working between them, it's entirely up to you. Okay, we're asked to find the linear and area scale factor of the similar shapes below. So what we've got is the volume. Now with this one it's slightly different. What I'm going to do is build up the table and work this backwards. So what we've got then are our two shapes, and we will find now a volume scale factor. So if we look at this now, what we're going to have is the following. Taking the larger one now, I'm going to divide this. This is going to give me my volume. So what we're going to do is take the 1472, so in the calculator, 1472, and we're going to divide that by 621. So this gives me, it's defined for the volume of each, 64 over 27, and that is a nice number. So the reason it's a nice number is because I can find the linear scale factor by taking the cube root of it. Remember, this is the volume, so here's my scale factor. So what I'm doing here is going from now going from the small to the large. So if we take the cube root of the answer, all we need to do is hit shift cube root of the answer. This should now give us 4 over 3. So we got 4 over 3, which is the linear scale factor. So 4 over 3. The area scale factor, we need to square the linear scale factor. So that will give me now 16 over 9. So all I've done is worked that out. So what we're going to end up doing, remember this is going from the small to the large. You can of course invert this and go the other way. If you wanted to go from the large to the small, it would simply be the reciprocal of these. So you can just write these the other way around. So let's say we were told now that we had, let's say that now the area, so the surface area of the smaller one, this one right here, was going to, let's just say it was going to be now 600. Let's say it was 600, and that would be, what have we got, miles squared. So if we wanted to find the surface area of a large one, we would simply multiply it by this right here, which is 4 over 3 squared. So we'd do 600 multiplied by the 16 over 9, and this would give us now the surface area of the large one. I've just made this up, but as you can see, often we're going to have to come back from one of these and go ahead and find the other scale factors. We're asked to find the linear and volume scale factors of the similar shapes below. So this time what we've got is the surface area. So we're told they're similar shapes, so we can go ahead and again building up the table. So we've been given now the surface area, so we're after the linear, we've got now the surface area, and we're also after the volume. So I'm going to now go from the small to the large. So what we're going to do is the following. 64 divided by 25, and that gives us now this value. So that doesn't simplify, 64 over 25. Remember, this is the linear scale factor squared. So if I take the square root of this, those numbers work quite nicely. The square root of 64 is 8. The square root of 25 is going to be 5. So this is the linear. We square it to get the area, and then we cube it to get the volume. So what's 8 cubed? 512. Let's write that there. The volume is going to be 8 cubed, which is 512, and then 5 cubed is going to be 125. Let's just check that. I'll take this, and then if I take the square root of this, this gives us the linear. That's the 8 over 5. I'm then going to take my answer, cube the answer, 512 over 125. So if we were told now that the volume of the larger one right here was going to be 100 kilometers cubed, and we wanted to find the volume of the smaller one, we could simply divide it now by this scale factor. So we'd have 100 divided by now the 512 over 125, and that would give us the volume now of the smaller one. So again, quite a nice question in terms of the numbers. They've worked out quite nice. We've got the squared scale factor, we need the linear, and we need the volume. Okay, the next one, it says two hollow cylinders are similar in shape. One is 12 centimeters tall and the other is 18 centimeters tall. We need to calculate the ratio. So this time we've got a ratio. The ratio of the areas of their ends, their volumes, and then in part C it says if the smaller one has a volume of 100 centimeters cubed, what is the volume of the larger one? So if we look at this, what we've got is 12 to 18. So I'm going to build up a scale factor chart, and what we can do is go ahead and put these as, now we can put them as scale factors and we can also put them as ratios. So if I'm looking at this now, let's go ahead. What we're going to have is a linear scale factor. We're going to have an area scale factor and a volume. So I'm going from the small to the large, and this is going to be the scale factor and this is going to be the ratio. So let's think logically right here. If I do 18 divided by 12, well, 18 divided by 12 is going to give me 1.5. So we've got 1.5, or we could say now that that is going to be 3 over 2. If we think about this now, we want the area, so we could write this now as follows. It's going to be 3 over 2 squared, which is going to give me 9 over 4, or we've got now 2.25. I like to write them like so, as my fractional work is better than constantly doing these. So 27 over 8 is going to give me now the volume scale factor. So if we look at this now, we can simply, let's just work out 27 divided by 8, what's that going to give me? Let's just quickly do that. Maybe I should know this. What are we going to have on here? 3.375. So 3.375. That's why I prefer working with the fractions. So if we look at this now, the ratio is going to be 2 to 3. This one is going to be 4 to 9. And this one right here is going to be 8 to 27. So we're looking now at the following. So the areas of the ends will be in a 4 to 9 ratio. The volume now will be in an 8 to 27 ratio. In part C it says if the smaller one has a volume of 100 centimeters cubed, what is the volume of the larger one? Well, we'll simply now take the 100 and multiply it by the volume scale factor, which is going to be 27 over 8, or if you like 3.375. And let's do that and multiply that now by the 100, which I should really have been able to do without that, which gives me now 337.5. So 337.5, and that will be centimeters cubed. So all I've done is gone ahead and worked that out. You can go in the opposite direction. I prefer to scale up and get this scale factor of 1.5. If you're unsure what I've done just here, this is the linear. I've simply squared both of these, or you can just write it from a fraction. So squaring 2 gives me 4, squaring 3 gives me 9, cubing 2 gives me 8, cubing 3 gives me 27. Okay, next one. A cylindrical can of height 15 centimeters holds 1 litre of orange juice. What height to the nearest millimetre must a similar can be if it holds 500 millimetres? Okay, let's pick out the information that's important here. We've got a volume scale factor to work with, 1 litre, and we've got 500 mil. So what we've got here is a scale factor. So you can work it forwards or you can work it back. What we can say now is the following. We've got on here a volume scale factor. So the volume scale factor is going to be 1/2. So what we need to do to get the linear scale factor now is take the cube root of this. So what we're looking for now is the linear. We're trying to match this up, and let's just grab this. We've got now a height of 15, and we're looking now the height of this one right here. So we have the volume scale factor. The volume scale factor is a half, so the linear scale factor is going to be the cube root of 1/2. So if we go ahead and do that, let's find now the cube root. So taking the cube root of a half, that's going to give me now this value right here. So what we're going to have then is the following. We're going to have now 15 multiplied by the cube root of 1/2, and that is going to give us following. And we need to be careful here to the nearest millimetre, so let's do 15. So if I do this, now what I could write is that this is going to be 150 millimetres, just to make my life easier. So multiplied now, this will already be in millimetres. You can do it in centimetres if you like. So that's going to be 119. Let's just change that over. What have we got? 119. And let's just write this on. 119 millimetres. And that now is correct to the nearest millimetre. So 119 millimetres. And that is now to nearest millimetre. So let's just pop that in. So nearest millimetre. And just check that that all works nicely. Yeah, so that looks good, and that is going to be the final answer. Okay, let's do one more. Some information about the surface area and volume of two similar solids has been given. We need to find the missing value. So what we have here is the surface areas. We've both got those, and then we're looking for the volume. So what I'm going to do is find the area scale factor. So if I think about this now, what I'm going to have, and of course we could build up a table, you don't need to, but we can do that anyway. So if we look at this now, what we're going to have is the linear, so that's just the straight line. We can have the area, or in this case the surface area, and the volume. So if we look at the scale factor, we've got now 68 divided by 17. 68 divided by 17 works out quite nicely, which is going to give us 4. So if we think about now the linear, this is going to be the square root of 4, which of course gives us 2. We then now, and I'll just put this here, this is going to be 2 squared, and of course we should hopefully now know that this one is going to be 2 cubed, which is 8. So I've found the area, I've square rooted it, and now I'm going to multiply up. So all we need to do, or raise it to a third power, the volume that we're looking for is going to be on here. Now, just consider we're going from the larger one, so we can say this is going to be 160, and we're going to be dividing by 8, or 2 cubed. So if we go ahead and do that, so we've got 160, and we're going to divide that by 8, which gives us 20, and we can write that on. So if we write that on, I don't know why I did it on the calculator, that will give us now 20, and that will be yards cubed. So we can see now how significantly small it gets given that we've got these scale factors. So there we go, that's some work now looking at the linear, the area and the volume scale factors of similar shapes or similar solids. Building up the table might help you out. With this one, what I've done is look at going upwards, so of course all I've done is divided. You might want to go the other way and say that it's a 1/4 and then work backwards, but it's entirely up to you. The logic should kick in when you realise that if you multiply this by 8, quite clearly the volume of the smaller one is not going to be 8 times the volume of the larger one. It's going to be 1/8.